Hey everyone, and welcome back to the channel. Today we are going to be making a video on MapReduce, which frankly I'm extremely glad is not going to be nearly as long as the one on Dynamo because I was starting to die when I was recording that. MapReduce is a topic near and dear to my heart, as is CrapReduce, which I'm going to start having to implement a little bit more at my job recently. Been spending a lot of time in the handicap stall. But yeah, forget about that. I'll do that on my own, and we can go ahead and learn about some distributed systems. So let's go ahead and get into it. Alrighty, let's go ahead and get into things. So as I mentioned, today we're going to be covering the MapReduce paper. Now, the nice thing about a video like this is that once again, MapReduce is a subject that I've covered on this channel extensively in the past. And so what that means is, as opposed to having to spend too much time talking about the semantics of MapReduce or what exactly the motivations for creating it are in the first place, I guess what I can really try and think about more is contextualizing it within the history of why it was created, right? So what its use cases were at Google, specifically around the time that it was made. And so that is really what I'm going to look to focus on a lot. So in order to talk about that, first I guess I have to give some context for the paper. It was created at Google by Jeff and Sanjay. It was released in 2004. And it's basically a very important inspiration for a bunch of open source software. So it's hugely important for Hadoop because MapReduce is a major piece of that. They basically recreated it based on the paper implementation as far as I'm aware. And then additionally, it is a precursor to Apache Spark, where Spark is pretty much now what people use a lot more for modern day batch processing. So obviously MapReduce does have some downsides, which I've spoken about plenty on this channel. I'm not really going to focus on those that much in this video. I'm simply just going to focus on the paper itself because there's a lot to be learned from it. So just as an introduction to talk a little bit more about setting the scene, basically Google has a lot of intensive batch jobs, right? So, they compute things like the most popular queries of the day. They pretty much scrape the full web, and then in addition to scraping the full web, they use an algorithm to basically index it and rank all of the web pages, right? They're building that PageRank algorithm so that you can use the search index to find what's most relevant to you. And so basically every single one of these jobs is going to be distributed. It's impossible to run all of this computation on a single node, so they put it in many places. And I guess the problem was, up until around 2004, what this really meant was that all of these different jobs had a ton of different boilerplate code, resulting in doing, a bunch of similar things. And the similar things that they were doing were pretty much the complexity of distributing your workloads, right? So, retrying failed tasks, load balancing to make sure each node is getting a similar amount of work to do, and also scheduling tasks, picking out a node that is not so busy to actually go ahead and perform that task, are all problems that pretty much all of these batch jobs aim to solve individually. And of course, whenever you have a bunch of diverging workflows doing the same thing, you want to try and standardize that. In addition, we can just save developers a lot of time. The truth is, most people are not that great at programming with distributed systems. I can tell you from my little bit of experience doing it at work that it's freaking hard, and I miss a lot of edge cases. And so it's always very nice when you can just go hit an API and it does everything cleanly for you. And so that's pretty much what Jeff and Sanjay set out to do. So let's quickly talk about Google's compute cluster as well, because I think that's also going to give us a much better sense of why they made some of the design decisions that they did. So they're using commodity hardware, which I think was not necessarily even the trend at this time. There were a lot of people who did do vertical scaling, and as a result, using just a bunch of relatively normal computers, and a ton of them was something that was fairly unique, and you had to work with that. So they're all connected by Ethernet within a data center. You'd have some sort of network switch. They're all using these cheap hard drives as opposed to anything fancy. And because we have thousands of these machines all throughout data centers, failures are common. It's even possible that in theory a full data center could go down, right? It's a similar setting to the Dynamo paper, which was written at a similar time. And so these computers, in addition to always being running, they might even be running multiple different jobs at once. Like I said, Google has many, many different batch jobs, and they're probably going to be running on the same cluster, and as a result, competing for resources. Nice little brain fart there. It's after work, so I'm dying. Cool. So Google notices that they are constrained by their network. This is going to be a very important detail for later in the video when we see how they try and optimize their software for the fact that they are network constrained. Okay, so let's go over a very, very high level overview of what MapReduce is. Basically, they invent this, and the gist is all it does is take in a bunch of input files on their distributed file system, which is called GFS, we're going to make a video devoted to that, but same thing as Hadoop basically. You've got a bunch of different nodes holding files, they're replicated, you've got one sort of name node which is holding the metadata. And then in addition, once this job is done, this MapReduce job, all it really does is going to produce a separate immutable set of output files, also in GFS, that you can then access and use as a database index or something like that. Cool. So the inputs, put pretty simply, are just going to be a pair of key value, or basically a list of key value pairs, and then also an output is just going to be a list of key value pairs. And so typically, at least when this was first created, they weren't doing this with like some sort of like Avro or protocol buffer input or something like that. I think it's since been adapted in order to support all of these, but at first when it was created, they were just input in terms of text and output in terms of text, and then there would be functions or code that would understand how to parse those text files. Cool. So now the question becomes, okay, well, we've got this concept of a MapReduce job. If I'm a developer and I'm trying to use this MapReduce API, what do I actually have to give it? So the first thing that we actually have to provide it with is a mapper function. So the map function basically takes our input data and converts it to this intermediary key set, right? So we have this idea of our input data, just a bunch of random unstructured files in GFS, and then now we're making it slightly more structured, but local to that particular node. So we'll talk about that more in a little bit. So basically, for one input key and an input value in our actual input data, we're going to return potentially a list of intermediary key and value pairs. Hopefully that makes sense so far. So for example, let's imagine that we have a text file, right, where our key is the line number of the text and the value is the text itself. And let's say that our mapper function is trying to extract the word counts of every single line. An example of a mapper function would basically be taking all of these guys and then returning the count of it. So in this case, there's one Jordan, there's one is, there's one sexy, and in the second case, there's one Jordan, there's two ises in that sentence, there's one not, there's one who, two he's, and one thinks. Hopefully the map function is making sense. I'm sure you use it in your day-to-day coding job all the time. You're literally taking something and you're mapping it to a different value. Cool. The next piece of this is going to be the reduce function. So the reduce function is basically going to take in a bunch of sorted key value sets, right? So the idea there is that you sort all of the intermediary keys and their corresponding values, and then you basically compute a value for every single intermediate key. You squash all of those values for it together, combine them, and then return one value per intermediate key. So basically the idea is if we want to specify some sort of spec for the reduce function, we take one intermediate key, we take the list of values that it has for it, and then we return that key and its actual final value. Cool. So the idea now is, if we take the output of what we had before and we combine basically these two mapping outputs, so we combine the whole intermediate key set. Now what we have is, and we're alphabetically ordering the keys. We've got he over here is present twice, Jordan is present twice, not present, sexy, thinks, and who, because we're ordering them alphabetically. And so the reduce function in this case is basically, sum up all of those counts. So he ends up with 2 because there was only one key for he and it was 2. Is going to end up with 3 because these guys get combined, and so on. And so that is ultimately going to return us the final word count of each word. Now the really nice thing about this mapper and reducer function is you can think about it yourself, but you can express all sorts of really complex code and really complex functionality via just providing 2 functions. Everyone's honking outside of my window, the traffic situation is terrible. But the gist is, basically, you can get a ton of flexibility out of just specifying a map and reduce function, and as a result of doing all of that, Google is able to enable its developers who are just familiar with this, map and reduce API to build out these really complicated distributed jobs. Cool. So we understand what mapping and reducing is, but now let's talk about a very high-level implementation of how it's done under the hood, right? Because we're abstracting all of this away, but we want to understand how it actually works. So for starters, I guess the gist is, we've got these mapper tasks that the developer passes in. Like I mentioned, that runs on every single line of input data, and that's going to generate our intermediary key set. Next, we have all of these intermediate keys. Let's imagine that, all of these mapper tasks are run on a bunch of different distributed nodes within the cluster. So we've got many nodes running mapper tasks, and many nodes now have intermediate keys. So locally, what we're going to do is actually sort those, right? All of the intermediate keys so that the same key is next to each other on the mapper node. And then what we're going to do from there is we're going to break them into partitions. So I'm going to discuss in a little bit how we actually break those keys into partitions, but it is going to be based on the intermediate key value, or rather the intermediate key itself. And then now we've got a few partitions on every single mapper node. The next thing that we're going to do is take all of those partitions of the intermediate key set and sync them to our local disk on the mapper node. After that, what we're going to actually do is go ahead from the reducer node and fetch all of the partitions that we want for that particular reducer node. So every single reducer node is going to claim one partition of the data from each mapper node, and it is going to then perform the reducer task. So we'll talk about that a little bit more in a bit. Finally, the reducer is going to merge together all of the sorted lists, right? Because it's getting data from every single mapper node. We're doing a shuffle phase here, and then merging them together so that the order stays sorted. Then after that, the reducer function is going to run on every single key and its associated values. And then finally, the ultimate output of our reducer function on every single reducer node is going to get sunk to GFS. And what that really means in this case, most importantly, is that it is getting synchronously replicated so that we make sure we don't lose that data. Cool. So that is how MapReduce works at a high level, and I have many diagrams that we're going to show in a little bit to make sure that we understand it a little bit better. But I want to quickly talk about a couple of other developer inputs that you're going to have to provide when making a MapReduce job, because this is important for kind of setting the scene. So number one is this concept of a number of output files, right? I mentioned basically that all of those are going to be sunk to GFS. And then in addition to that, basically, we've got all of these separate reducer tasks. So basically, the number of output files that we choose, we create one reducer task per output file. And then in addition, what that means is that if we have one reducer task per output file, every single mapper is splitting its intermediate key set locally into our different pieces, because each one of those pieces is going to be sent to one of the reducer nodes. So like I mentioned, now every single mapper task is going to be storing our files locally. Because it does its local mapper, it partitions the data as necessary, and then each partition gets sent to the appropriate reducer node. So how do we partition that data? Well, the developer also provides a partitioning function. So basically the gist is, you can be smart about this because maybe for whatever reason we want the same key in the same output file. So you may want to partition keys in a way such that that actually happens. But the gist is typically it's going to rely on some sort of hash function so that we can make sure that we're load balancing keys appropriately. And the gist is it takes one of those intermediate keys, which is the result of a mapping function, and it places it into one of the R buckets that we create on every single mapper node. Another thing that you can do if you're concerned, hey, it's possible that we have one key that has a ton of entries and most others don't, is you could actually run basically an initial MapReduce job to perform some sort of sampling on the data to maybe get a better sense of what you're going to provide with your actual partitioning function for your actual MapReduce job, not the sampling one. Cool, and then the last piece of this is also going to be the size of each input file. So I guess you do have files in GFS, but MapReduce is going to split them all into a bunch of chunks. Each one is typically going to be 16 through 64 megabytes. And then once all of those chunks are determined, which is done by the client that actually hits MapReduce in the first place or calls the MapReduce API, now all of a sudden we split it into M pieces, right? We take the input, we split it into a bunch of 64 megabyte chunks. Now we have M chunks. And so we're going to be using this M parameter a lot because M is actually going to be the number of mapper tasks. Each chunk itself is going to be handled by one mapper task. Now each node might run multiple tasks, but a task is kind of the unit of work in MapReduce. Cool, so here is our implementation overview. So let's imagine we have M equals 3, right? So that means 3 map tasks. And similarly, we have R equals 2, which means 2 reducer tasks. It also means 2 output files. It also means that each mapper stores 2 local partitions of its mapped data. So let's go ahead and take a look at what this looks like. So like I mentioned in the note right here, in reality, nodes in our cluster may run many mapper or many reducer tasks. But in this example, each mapper is going to be on a different node, and every single reducer task is going to be on a different node. So let's go ahead and start this thing out. We've got 3 mapper nodes over here. They're basically going to schedule their map tasks, and the first thing they're going to do is look at their input data over here. They're going to map it according to the mapper function. They're going to partition it according to the passed-in partition function that the developer program actually gives us. They're then going to basically locally sort every single one of those partitions, and then they're going to sync it to local files. So right now, after a mapper task is done, as you can see, we have these local files on the mapper node, and so what we can then do is go ahead and write over to our master node over here. Now I'm going to zoom in pretty aggressively for 1 second, because you can see what the master node is basically storing is the file paths of all of the outputted mapper tasks. So it's actually not just storing one file path per mapper task, but it's storing one file path per each partition of the mapper task. So recall there are 2 partitions for reducer tasks, or rather there are 2 reducer tasks in total, meaning that every single mapper task is going to have 2 partitions to it. So you can see that we have a file path for mapper task 1, reducer task 1, mapper task 1, reducer task 2, mapper task 2, reducer task 1, mapper task 2, reducer task 2. Cool, so hopefully that is starting to make sense. Now the last piece of this whole thing is basically what's going to happen now in the next step is that our reducers, which are over here, are going to get notified of the fact that the data that they want is available. Now the reducer can actually go ahead and say, okay, well, as I see the file paths of the places that I need to read, I have to go back to the mappers and actually read it. So for example, this reducer R1 over here has to read the R1 partition on mapper 1, on mapper 2, and mapper 3. And R2 has to do the same exact thing because it also needs to read partitions from every single mapper. So this is what's known as shuffling. So it reaches out to these 3 guys, it gets the data, it performs the reducer tasks, it lets the master know the locations of the reducer tasks once they're finished. So it gives some GFS address for R1 and R2. And then finally, once the master sees that it actually has these, it can go back to the user program and say our job is complete. So hopefully at a high level that is starting to make a lot more sense. However, there's still a few more unanswered questions or finer details that we want to get ourselves into. So first off, like we mentioned, Google is network constrained. So what are a couple of the bandwidth optimizations that they do in order to deal with that? Well, for one, basically, like I mentioned, when you're running a mapper task, you're only writing to local disk. We're not writing to GFS as after the result of a mapper task, the reason being that writing to GFS means that you have to basically synchronously replicate your data to multiple places, and that's quite expensive because now you're sending all of your data over the network as opposed to just writing to local disk. So that is a pretty big thing right there. That being said, it also makes us kind of susceptible to node failures because if our mapper goes down, or the node that ran the mapper task goes down, the result of that mapper task is also gone. And so we're going to have to be able to handle that failure situation. Number 2 is that mapper tasks will typically be scheduled near or on the same exact node where input data is stored. Basically, we are aware of which computer has the hard drive which is holding input data, and we can schedule the mapper task either there or if it's super busy on a computer that is at least in the same data center. Another thing though, which I suppose is a downside of this, is it means that basically, every single hard drive that we have or every single computer as it continues to increase in hard drive space and stores more files, it's more susceptible to, basically getting scheduled more tasks on it. So typically now what we want to do is scale our compute resources similarly, if not linearly, to our storage resources. And at least in today's computing environment, maybe this is a little bit less practical, but evidently they were willing to take that trade-off back then. And then the last piece is something called a combiner function. So note, for example, our map task, right? So we had this example right here. Let's imagine this was all one map task, and we were about to send all of this data over the network to a reducer node. Well, what we could do before actually doing that is we could actually run the reducer function effectively on the map node before sending it over anywhere, because we might be able to do some combining before actually sending that data, thus making the file size smaller, and again, thus kind of using less network bandwidth. So the combiner function is basically running the reducer function on the mapper after doing the mapping and putting everything into its own partitions. Cool, hopefully that all makes sense. So another thing to talk about is the master task. Now what I find interesting here is obviously in the Dynamo paper, Amazon is very adamant that they really don't want to have a single master node. They're like, we want everything to be running the same exact program. It's easier to reason about. It is less prone to failures. On the other hand, basically Google is totally fine with having a master node here, and they find basically that it makes their life a lot easier to do the scheduling through that master node, to basically use it as the source of all the metadata for the MapReduce job. Now, to be fair, I think part of this is that for something like Dynamo, that is potentially a client-facing service, and you want it to be running at all times. Whereas with something like MapReduce, it's for batch jobs. They can fail in the background. They can be restarted. Maybe we're a little bit more willing to kind of take a shortcut here and just use one centralized node in order to schedule everything. So what is the master task actually going to be doing? Well, for one, it is going to be scheduling all of the map tasks and all of the reduce tasks. So since it has to schedule a map task for every M of them and a reduce task for every R of them, and potentially reschedule some that fails, it's going to be scheduling O of M plus R tasks. Additionally, in order to tell if things are working as expected or if a certain task is down, the master node basically will heartbeat all of the worker nodes that are running a mapper reducer task and then restart them accordingly. Cool. Another thing that it's responsible for is storing file locations. So as I mentioned, when we go back up here, we are storing all of the intermediate key set file paths in the master node, and we're also storing the output file paths in the node. So that is going to be potentially a lot of storage. The reason being that as far as the number of intermediate key set files that there are, there's actually going to be R partitions per mapper task, so per M mappers, which means we have O of M times R total temporary files basically that are locally stored on a mapper node that our master task has to be aware of. And so that can potentially be a lot if R and M are really large. In practice, it's not too bad because apparently, according to Google, each one of these key set or intermediate file names is only around a byte. And so they can easily store it even if they have, even if M times R is like a billion or something like that. Another thing, like I mentioned, got to store the final GFS output. And then finally, it also has to notify the user program when things are completed. Cool. Let's go ahead and talk about fault tolerance a little bit, because this is one of the most important parts of MapReduce. It's a massive cluster that we're running these jobs on. At least one node is likely to fail. So how are we going to go ahead and deal with that? So let's say a reducer node goes down. When a reducer node goes down, like I mentioned, the master node is heartbeating it. It can tell when that happens. The master node will then just reschedule that task elsewhere. It'll just have to go ahead and get all of the mapper output data and then rerun the reducer task. Let's say that a master node goes down. This one is pretty problematic because even though Google admits in the paper, hey, maybe we could build some checkpointing into the master node itself so that we could easily restore state, they prefer to just cancel the whole job. Let the client who is calling the MapReduce job in the first place detect that the master node is down, and then restart the whole thing. Like I mentioned, these are batch jobs, so it's not crucial that they have to be up at all times. If things do fail, we can restart them. It's not ideal to waste a bunch of time, but Google evidently feels, all right, there's just one master task. It's pretty rare that that one task is going to go down on a given MapReduce job, so we don't have to consider this case too much. Number 3 is that a mapper goes down. So this is what I would consider a pretty interesting scenario. The reason being that if you recall, when a mapper completes its job, it only syncs its output to local disk. It's not replicated anywhere. So we actually lose that state when it goes down. So let me go ahead and show what this might look like in practice. Let's imagine that node A is running 2 mapper tasks. So it's going to go ahead and sync these output files, And it's actually going to make 4 of them because each mapper task is going to have 2 reducer partitions that it has to create. Cool, so node A now has 4 total partitions living on it, and let's say that R1, which is the node running reducer task 1, is able to load those off of A and completely run its reducer task. On the other hand, let's say R2 starts loading that data, however it isn't able to completely get the files locally before node A fails. So what do we do now? Well, keep in mind this guy has been heart beating with the master, and the master is going to see that those mapper tasks went down. It's then going to say, shoot, if the mapper went down, I have to go ahead and restart this. Fortunately, since there are 2 mapper tasks, we don't actually have to put them on the same node in the future. We can actually distribute that workload to 2 other idle nodes and have each of them run 1 mapper task. So instead, now, after this thing gets restarted, maybe 1 mapper task gets restarted on node B, 1 gets restarted on node C. And each of them is going to output 2 intermediary files, right? Because 1 for each reducer partition. So what this is going to do is then push over to the master node. The master node is now, as you can see, has the new file paths for the restarted mapper job. And then, from there, reducer 2, since it hasn't completed its reduction job yet, reducer 1's fine, since it already has, doesn't need to rerun this. Reducer 2 is now going to hear from the master node, reach back out to B and C, get the data as necessary, and run the reducer function. Cool. So like I mentioned, A's mapper task can now be distributed between B and C. And the problem with this is that if that mapper function for those 2 mapper tasks was not deterministic, now it means that the output of R1 was from the earlier invocation of the mapper job, which again, if it's not deterministic, that's going to be a different result than what R2 was running on. So keep in mind, this is why we always do want to make our MapReduce jobs deterministic and idempotent if possible, but you can still choose not to do that. You're just going to have to face some consequences. Cool. Another thing that is very central to the concept of the MapReduce paper is this idea of stragglers. So basically, Google finds that whenever we have a massive compute cluster, some computers are just randomly going to be really slow. One example that they give is, maybe it's running a bunch of other tasks. Like I mentioned, these are shared resources. Another is a software bug. They mentioned one was basically like there was a software bug that stopped a CPU from using any caching and it slowed down significantly. And then there could also be hardware bugs on the disk or something like that, and that might greatly slow things down too. So what Google does to actually counteract this is basically when our MapReduce job is down to the last few tasks, so maybe a few mappers left, a few reducers left, could be both, the master is basically just going to schedule redundant invocations of them. Keep in mind that because everything should be idempotent, it's totally fine to just run these things twice. And so basically what they find is that this helps them eliminate the long tail of their jobs, right? They can see that if they don't do this redundant scheduling, a few tasks can run significantly longer than the rest of them, and actually so much so that in one particular benchmark, those tasks were running 44% longer when not using this redundant task scheduling. So they basically cut down on about a third of the total MapReduce time spent by basically scheduling a few redundant jobs for the last few tasks. Okay, another thing that I want to talk about is actually tuning our parameters, right? As a developer, you're responsible for choosing a few things like M and R and stuff like that. And so how can we actually choose these to be the best possible values? In practice, Google finds that they want the number of tasks to be much bigger than the number of workers. Why is that? Well, it's going to allow us to do more granular task scheduling. So to make an example of this and why it enables us to load balance a little bit better, let's imagine that we've got 4 tasks that we want to schedule. Each one is pretty big in terms of the amount of computation that needs to be done, and each is going to add 4 load. Then over here on the bottom, we've got 4 different nodes, which start with load 5, load 6, load 7, and load 8. The best thing that we can do to balance out this load is to assign 1 task to each node. And now, as you can see, after doing that, we're pretty balanced, right? We have one with 9 load, one with 10 load, one with 11, and one with 12. However, when we have more granular tasks, we can actually get an even better distribution of load. So in the same example where the nodes start with 5, 6, 7, and 8 load, if we have 16 tasks where each is adding 1 load, so still a total of 16 load to distribute like the last example, this time what we can do is add 6 to this guy over here, we can add 5 to this guy over here, add 3 to this guy over here, and add 2 to this guy over here. And so that way we've distributed all 16 tasks, but when you look at the actual difference in terms of the load between those 4 machines, it's less spread out on the right than it is on the left. So more granular tasks allows the master node to actually check on the status of each node first and basically make smarter decisions about that. So M plus R, hopefully that makes a lot of sense, but what should we choose for R, right? Because that is something that we very explicitly choose. Well, typically we don't want it to be too big, the reason being that every single R that we choose, or rather the bigger the R that we choose, the more files that we have to write to GFS, and that's expensive. So typically we want it to be a small multiple of the number of workers that we're going to be using on our batch shop. If we have 5 workers, something like 10 or 15 as the number of GFS files that we write seems pretty reasonable. The last piece of this is if M and R are super, super big, recall that the master node still has to store a bunch of metadata. In fact, it has to store M times R metadata rows for each of those tasks because we need the intermediate key set path after we perform our mapper task. And so even though these are all 1 byte, so it's probably not too big of a deal in practice, you know, if you have like I don't even know what's after trillion, a quadrillion of these intermediate paths to store, maybe we start getting in trouble a little bit. Okay, so we're finally reaching the end of this thing, which is good because I didn't talk for 45 minutes this time, but 30 is still not too bad. Let's go ahead and talk about the impact of MapReduce, because again, that's what we really care about, the motivation and what it got done. So basically, within a year of releasing MapReduce at Google, over 900 jobs got written. So that's pretty impressive considering how many people were at Google at the time. And just, you know, it speaks to the pace of development and how quickly you can write these MapReduce jobs. So typically on those 900 jobs, there was an average of 157 workers. So that's definitely not small. You can tell that we're doing a lot of big data tasks. And on average, 1 worker death per job. So even though that doesn't seem like a lot, if you're not properly equipped to handling node failures, this is basically going to take down every single job. It means that most jobs would have to deal with a node failure, and you would have to completely restart most of them otherwise, which would be bad. So on average, out of those jobs, they typically had 3,000 mapper tasks, around 50 reduced tasks, and just doing some hand-wavy math, that means probably around 150 kilobytes of memory on the master task, which is not a lot at all. That's very manageable. Cool. They also claim that even besides just, you know, the popularity of MapReduce in Google, it made the code a lot simpler to read. So for their actual main indexing code, right, the stuff that really is backing their search engine, they were able to basically convert it to a sequence of 5 to 10 changed jobs from MapReduce. So, right, you finish one MapReduce job, you pass the output of one as the input to the other, and they found that the performance of all of the chaining was totally good enough that they could keep it this way and keep their code a lot simpler. You know, if they really wanted to optimize their code, what they might do instead is try and combine all of the mapping logic and all of the reducing logic into some really complicated functions so that they could get one pass over the data. But they found that wasn't actually even necessary in real life, and as a result of that, it made their code much cleaner, and it took them days instead of months to start adding new features to their code. So obviously very significant. The last piece of this is that, like I mentioned, simplified code a ton, went from 3,800 lines in one particularly complicated segment to 700, which is no joke at all. So let's go ahead and get some main conclusions out of this paper because I think there are a few that are unique to the Dynamo paper. For starters, I think one, it just speaks to how great the functional programming model is and, you know, how when you can use it, it's something that is good to use. You can express a lot of complicated functionality with seemingly simple functions. Number two is that distributed computing is hard. That's the reason I spend so much time studying it and still am ass at it. But the gist is, especially for people who are writing code and trying to do so on many different computers, you don't really want to have to deal with partitioning, race conditions, fault tolerance, all this other stuff. And so being able to basically abstract this for the majority of your developers and provide them with a simple model to get the functionality that they want can be extremely impactful. So the term that the Google writers used was restricting the programming model. They're not the first ones to do this. They took inspiration from other papers, but it obviously worked out extremely well for them. And then I think finally another big takeaway here is that regardless of what software is actually best for you in theory, the one that's best in practice is whatever works with your compute environment. In Google's case, basically their computers were network constrained. In today's case, it seems our networking hardware has gotten a lot better. And nowadays, when it comes to modern analytical databases and running big batch jobs, it seems we're actually more CPU constrained than we are network constrained. But nonetheless, you can see the optimizations that they use to actually deal with that, like data locality for mappers, local rights for intermediate data, and also things like combiner functions. And so overall, they have to cater to what they're running on, and that is really what's most important. Anyways, guys, hope you enjoyed this video and found it informative. I'm going to hope to get outside a little bit and actually touch some grass, so I will see you for the next one.